Okay, so complex eigenvalues. So to deal with complex eigenvalues, we have to do a little bit of complex analysis. Remember that the characteristic equation is something like this. So if we solve this, what do we get? We get r equals negative b plus or minus the square root of b squared minus 4ac, a is just 1, all over 2a. So r is minus 8 plus or minus the square root of 64 minus 100, all over 2. And r equals minus 8 plus or minus the square root of minus 36, all over 2. And we have a way to handle these sorts of things. A minus sign inside the square root is I squared. We use the letter I for I squared equals minus 1. So r then is minus 8 plus or minus I squared times 6 squared inside our square root, all over 2. And so if we take our square roots, what have we got? Minus 8 plus or minus I times 6, all over 2. So r is minus 4 plus or minus 3i. So the I there is the complex number, I equals square root of minus 1. In the quadratic equations, we see that complex roots appear in what are called complex conjugate pairs, a plus or minus ib. So here I've got minus 4 plus 3i, minus 4 minus 3i, and the only difference between those two is the sign on the term that has the I. So just as a little review of complex numbers, you can add them, multiply, divide. So addition is just adding like terms. So 1 plus 2 is 3, 3i minus 5i, 3 minus 5 is minus 2i. Multiplication, you do that by foiling. 1 times 2 is 2, 1 times minus 5i is minus 5i, 3i times 2 is 6i, 3i times minus 5i is minus 15i squared. To tidy this up a little bit, we can have the 2 minus 5i plus 6i is plus I squared, remember that I squared is minus 1, so this becomes minus 15 times minus 1. 2 plus I plus 15, which equals 17 plus I. So what about 1 plus 3i over 2 minus 5i? Well, we use a very nice fact about complex conjugates. What is 2 minus 5i times 2 plus 5i? It's complex conjugates. 2 times 2 is 4. 2 times 5i is plus 10i. Minus 5i times 2 is minus 10i. Minus 5i times 5i is minus 25i squared, but I squared is minus 1. So what are we left with? 4, these terms actually cancel out. This becomes minus 25 times minus 1, which is 4 plus 25, which equals 29. So if I take this and I multiply it top and bottom, if we're coming back to this division now, and I multiply top and bottom by the conjugate of the bottom, what do I get? So 1 plus 3i times 2 plus 5i. 1 times 2 is 2. 1 times 5i is 5i. 3i times 2 is 6i. 3i times 5i is 15i squared. What are these two multiplied together? That's this nice fact. It's just 29. It's a real number because the imaginary parts canceled out or became an I squared. So this is minus 15. 2 minus 15 is minus 13 plus 11i over 29. So we can do division, and you can do subtraction too. It's just like addition. What are the powers of I? What's the pattern? Well, we know I to the 0 is 1 because anything to the 0 is 1. I to the 1 is I because anything to the 1 is itself. I squared is minus 1 because we defined it that way. I cubed is, well, I cubed is I squared times I. So it's minus I. What's I to the fourth then? Well, I to the fourth, take this equation, multiply both sides by I. That'll give you I to the fourth on one side. On the other side, it gives you minus I squared. But I squared is minus 1. And minus 1 is actually 1. Another way to look at it then is just square both sides of this equation. I squared squared, that's I to the fourth, minus 1 squared is 1. But then that tells me what I to the fifth is. I to the fifth is I to the fourth times I, so that's just an I. I to the sixth, take I to the fourth multiplied by I squared, that's 1 times minus 1, that's minus 1. I to the seventh is I to the fourth times I cubed, so that's minus I times 1, that's minus I. I to the eighth is 1, I to the ninth is I, etc., etc., etc. Where's I to the 137 in this pattern? Well, 137, we can write it in powers of 4. It's actually 4 times 34, 16, 4 times, yeah, 34 plus 1, right? 4 times 34 is 120 plus 16 is 136 plus 1. So if we start with 4, 0, 4, 8, dot, 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 I to the 136th, right? Because that's 4 times 34. Then I to the 137th will be in this row. That's equals I to the minus 1 should be in this row, right? I to the minus 2 here, I to the minus 3, I to the minus 4, minus 4, 0, 4, 8, minus 3, 1, 5, 9. So this is minus I. That's a useful thing to remember because we often get i's in the denominator, and it's a minus I. So some basics about complex numbers. Euler's formula, also an important thing. You can do this with calculus 2. E to the ix is cosine x plus I sine x. Here's the Taylor series for e to the x. For cosine x sine x, we just plug in ix into the formula for e to the x and grind away, and you find out what that is. So we want the solutions to this differential equation. And I think we solve that equation, r squared plus 8r plus 25 up there. So our characteristic equation is r squared plus 8r plus 25 equals 0. And we found that the solution was r equals not entirely remember what that is. Minus 4 plus or minus 3i. So what are my two solutions? I'm going to call them z because they're complex, and I don't want to use, I want to use y for real ones. But z1 of t is e the eigenvalue times t. And a second one is e to the other eigenvalue times t. Okay, so those are solutions. You can plug them in, grind through it, and check them out. They are, in fact, solutions. They're not solutions we want because we don't want solutions that have eyes poking around in them. But we can rewrite these using Euler's formulas. Z1 of t is e to the minus 4 t plus 3 times I times t. That's just distributing this t. E to the minus 4t times e to the 3it, because I've got a plus sign here, so I can split up into two products. And I can use Euler's formula on that part now. So I get e to the minus 4t cosine 3t plus I sine 3t. Great. And z2 of t is exactly the same thing. E to the minus 4t minus 3it. So I'm just changing the sign from plus to minus. we grind through everything, it becomes e to the minus 4t times cosine minus 3t plus I sine minus 3t. And we keep in mind that cosine is an even function. So that means cosine of minus 3t is equal to 3t. And sine is an odd function. So that means the minus sign comes out of sine. We have that. And then finally, cosine 3t minus I sine 3t. So changing the sign on the I from plus to minus ended up changing the sign on the I from plus to minus down here too. So why are these two functions both solutions to this differential equation? Well, z1 of t, if we multiply it out, is e to the minus 4t cosine 3t plus I e to the minus 4t sine 3t. z2 of t, if we multiply that out, would be e to the minus 4t cosine of 3t minus I e to the minus 4t sine of 3t. Okay, so if I add these together, I get this, or 1/2 z1 plus 1/2 z2 equals e to the minus 4t cosine 3t. So why does this make this a solution to this differential equation? Well, this is a solution, z1. z2 is a solution, and linearity says if I take two solutions, multiply them by constants and add them together, I get another solution. So that means that that's a solution. Likewise, z1 minus z2 is 2I e to the minus 4t sine 3t. 1 over 2I z1 minus 1 over 2I z2 is equal to e to the minus 4t sine 3t. And again, linearity tells me that if I take two functions, multiply them, if I take two solutions, multiply them by constants, and then add them or subtract them, I get another solution. So those two things are solutions. So the general solution is going to be, we're going to use these two, e to the minus 4t cosine 3t and e to the minus 4t sine 3t as our basic solutions. And so if we get complex eigenvalues a plus or minus ib, then the general solution is k1 e to the at cosine bt, k2 e to the at sine bt. The a is in the exponent, the b is in the trig function. So here's a initial value problem. Solve this, sketch the solution, and comment on the shape. So characteristic equation, r squared plus 2r plus 6 equals 0. Solve that. R equals -2 plus or minus the square root of b squared minus 4ac all over 2a. R equals -2 plus or minus the square root of -20 all over 2. We can simplify that. R equals -2 plus or minus, well, the minus sign inside the square root is an I squared. The 20 is a 2 squared, which is 4 times 5. Right? So 20 is 4 times 5. That's 2 squared times 5. The minus sign is an I squared. So anything that's squared then can come out of my square root. And we get r equals -1 plus or minus I root 5. Great. So what are our solutions going to be? K1 e to the minus t, because the -1 goes up in the exponent, times cosine of square root of 5t plus k2 e to the minus t sine square root of 5t. So there's our general solution to this equation. We have particular initial conditions, y of 0 equals 2, y prime of 0 equals minus 4. So what are our k1 and k2? We can solve for that now. We've got y of t there, y prime of t. We're going to need that derivative. This is all differentiating now with the product rule. So we have minus k1 e to the minus t cosine of square root of 5t minus k1 e to the minus t square root of 5 sine square root of 5t. So to differentiate this term, we have to do the product rule, which means differentiate this first, that's this term, and then differentiate that term. The derivative of cosine is minus sine square root of 5t, and then differentiate the inside of the cosine. Plus, now we have to differentiate this term, and we'll get two terms for that again, minus k2 e to the minus t sine square root of 5t plus k2 e to the minus t square root of 5 cosine square root of 5t. Okay, so y of 0 equals 2. That means we take this equation up here, set y equal to 2, and then set t equal to 0. Keep in mind that sine of 0 is 0, so this term goes away because sine of 0 is 0, and we're just left with k1. Cosine of 0 is 1, so we're just left with k1 equals to 2. Y prime of 0 equals minus 4. Plug in minus 4 there for the y prime. And remember that sine of 0 is 0, so that just goes away. Cosine of 0 is 1, e to the 0 is 1, so we get a minus k1, and then plus square root of 5 k2. So I think I would be happier, and I'm going to make myself happy by doing this. I'm going to set that equal to 4, actually, because I want everything to cancel out. I don't want to have to deal with the square root of 5. So I'm going to make that 4. Y of 0 equals 4, y prime of 0 equals minus 4. So if k1 equals 4, that gives me minus 4 equals minus 4 plus square root of 5 k2, which makes k2 equal to 0. Good. So with that, our solution is y of t equals 4 e to the minus t cosine of square root of 5t. What does that look like? Well, keep in mind, if we want to graph this, that cosine of square root of 5t is between minus 1 and 1. So that means that 4 e to the minus t times cosine square root of 5t plus 1 here, minus 1 there, is between minus 4 e to the minus t and 4 e to the minus t. So what we've got is what's called an envelope, 4 e to the minus t up here, and minus 4 e to the minus t down here. And the function we're interested in is trapped between these two, and it's oscillating between minus 1 and 1. So our function actually starts up here and comes down and up and down and up and down and up and down and up and oscillates its way out. The amplitude of this is 4e to the minus t, which is decreasing as t is increasing, and it's oscillating from one edge to the other. And that gives us the graph of that solution.